Thank you for the introduction. Okay, thank you for the introduction, and also, yeah, it's nice to be joining Autoware Centers of Excellence. So I'll talk about my own work in the context of our bigger group here at TU Delft. So myself, I'm Holger Caesar. I have a background in computer vision, did a PhD with Vittorio Ferrari in Edinburgh. Then went into industry, worked for NuTonomy, later they were called Motional, for 4 years. So it's a robotaxi company that builds these self-driving cars that drive in Las Vegas and other places and drive people around. And yeah, for 2 years now, I've been back to academia, TU Delft in the Netherlands as an assistant professor, and still very much, as you say, working on autonomous vehicles. This is our group, the Intelligent Vehicles Group. So in total, we're 6 professors, and we try to really cover everything from machine perception to dynamics and control. We're also hiring 1 person for planning now, and then human factors, motion sickness, etc. And we have some nice facilities, self-driving vehicle platform, of course, a nice simulator, etc. And for those that have never heard of Delft before, so Delft is a small town, a little bit of like a miniature Amsterdam in the Netherlands between The Hague and Rotterdam. So if you want to visit us, you're always welcome to come by. One good reason to visit us might be the RSS conference, which this year is in Delft. And we're actually going to demo something there, which is a advanced vehicle summoning feature. So a bit like the Tesla, but more advanced, hopefully, in that it evades pedestrians, cyclists, etc. on the way. And this is very much built with Autoware. So we really wanted to go away from our custom in-house build to something more standardized and shareable, etc. Nicer architecture. Okay, now I want to talk a little bit about my own work. My overall research goal is, could phrase it as, how to collect, annotate, train, and evaluate sensor data more efficiently, and also, as Rahul said, at scale. So data collection sounds easy, creating new data sets. Annotation is especially auto-labeling, so how can we automatically label vast data sets? In terms of training, we're looking at lesser forms of supervision, but also foundational models. And then evaluation, especially also simulation as a tool for evaluation. And that's exactly what I will talk about today, although I do have to skip the training part since we don't have that much time. But yeah, maybe another time. So let's talk a little bit about data set creation. So you've already heard from Rahul about this NuScenes data set that we built. So this was the first kind of big industry data set. Was the first data set of that size, the first data set with radar. It also has nice 360-degree coverage, camera, LiDAR, radar, kind of everything you would expect nowadays. Also, semantic maps is also nice, especially for planning purposes. And yeah, this was fairly frequently used. And the data was from Boston and Singapore. Meanwhile, our group here in Delft collected their own little data set, a little bit smaller than what we have in NuScenes, but very interesting because it's in this Dutch old town. So you see these cyclists cycling around everywhere. Maybe Rahul is somewhere here in the data set, the other Rahul. And it's also the first data set with 4D radar. So that was quite unique. So you also have the elevation data. That's quite interesting data set to have. And then back to the company where I worked. At some point, we wanted to create a much larger data set. This is called NuPlan. So it's a ML-based planning benchmark. It's 1,300 hours from different cities. And again, this is auto-labeled data. So we did not label this by hand. This would have cost many millions, but instead we automatically labeled that. And the goal is really machine learning-based planning. So, it's a kind of an end-to-end model well, first of all, it's a neural network that does the planning, and then we also support the option for end-to-end models. So really models that take in images and output trajectories and just learn to drive that way. And the framework is nicely modular. You can plug in your own planner, agents, observations, controller, anything that you're working on, and can evaluate how the performance improves with that. Okay, now I talked about auto-labeling. Let's look a bit closer at that. So what we did for NuPlan, this is the same video again. What we did for NuPlan was to build a offline perception system. And this is similar to what also previous work done by Waymo and also by Uber. We just improved it further. The idea is basically you have an offline system that is very resource hungry, very slow, takes a lot of GPUs somewhere in the cloud. But therefore it's of course very powerful because it has those resources. And it doesn't have to be causal. So you don't have to just look at the past data. You can also look at the future data and kind of globally optimize that sequence. And that's how you get these nice quality boxes that I've just shown you. Yeah, here's kind of the overall setup of this perception pipeline. What we also did more for NuPlan was to extract scenarios. So in this case, unfortunately, no magic behind it. We kind of handcrafted 70 scenarios, 70 different types, and then we mined this large data set for that. So everything from like jaywalkers to following vehicles or lane changes after this. We have it all in there. And the idea is basically that you should not just evaluate on just driving straight most of the time, but you should be evaluating on specific scenarios to really see what is the performance of my planner on lane changes, what's the performance on jaywalkers, etc. And we also extracted traffic lights. So of course, you can use computer vision to detect traffic lights, traffic light bulbs. But what we did was to go with the motion. So we used the motion of these agents. And when they're moving, then we set it to green, the traffic lights. And when they're not moving, or when there's no observation, then we set it to red. Of course, it's not perfect, but it's quite nice. And that for your simulation, you get data from all sides of the traffic light, from the intersection, not just the one that you're currently looking at. So that's quite nice. Okay, going further in a separate work, we try to improve this kind of offline perception system even more. And we also worked on offline tracking. And in particular, we wanted to integrate the prior assumption, prior knowledge about object permanence. So this is something that young children cannot do yet, but adults know very well, is objects never disappear, right? They should always be somewhere. And I think it's more interesting if you look at the video. So you see that there was a bus somewhere here, but it now is occluded by this truck. And then towards the end, the camera actually shifts to the left camera. And then we see that truck again. In our method, you see also the view here on the map. It comes here on the map, follows this lane. And because our method has both a map as input, but also the assumption of object permanence, that's why we're nicely able to track objects even while they are occluded, which most of the other offline perception systems are not able to do. And that, of course, is very nice when you want a data set where you never actually lose tracks. This work is also on auto labeling. It's a little bit different in that it's mostly unsupervised object discovery. So the idea is, for most parts, we don't use any labels. And this data is actually from roadside units. So this is, for example, LiDARs that are mounted to traffic lights. So it's kind of static observer. And what we do is we kind of remove the ground plane, we cluster these objects, we do some tracking, and then also self-training to kind of have a detector that is a bit more consistent, because in the beginning, for example, static objects, you don't get them. But after a few steps of self-training, you do capture them. And then in the last step, we just fine-tune with a little bit of labels, here in this data set 1%, in this data set 5%. So it's typically something like 100 labeled point clouds. And with that, we get pretty good performance, relatively close to learning with the full data set. So that's quite nice. And it works so well because of this setup in this roadside units, where you typically have this elevated angle, you're looking down on the car, and then you really see kind of can easily figure out the whole size of this car, and thereby really capture it well. Whereas if your viewpoint is from a car, then it's a little bit harder because you don't see the back of the car. Okay. And talking about simulation, this is a recent work with SenseAct. So the idea here is we use neural rendering, a nerve-based method, to render a scene, the images from a driving scene that we've seen before. Then we have state-of-the-art end-to-end planning models, or AD models. So there are some recent methods called Uni-AD and VAD. They do exactly that, state-of-the-art on many tasks. They take in images and they output a trajectory. Then we have this trajectory, we go to a controller, we get acceleration steering, we have a vehicle model, and then we have a new pose where the car is going to be in the future. So you see this is closed-loop simulation. And then we can just render that new pose. And this way we continue on and on. And this way we can simulate really driving in photorealistic environment. And I want to show you this. This whole thing is called Neuro NCAP. It's inspired by the real-world NCAP tests, crash tests, but in our case, it's scenarios that we made up. So this is the original data set, normal driving scenario. Now we go back and we have three different scenarios. One is a car is static, so the car is just parked here and you need to avoid it. And the other scenarios are here on the left side, a car comes racing towards you. And on the right side, a car comes here from the side. So it's static, frontal, and side. And then we just run these state-of-the-art planners on it, and we see that half of the cases, they crash, which is very shocking. But we hope that with this kind of standardized benchmark in the future, people will develop better planners. And the idea is, of course, they are doing not so well because they've never seen these kind of crash scenarios. So maybe by training for these scenarios, we will be able to develop planners that are able to cover these scenarios. Okay, then moving on. Okay. A few other topics that don't really fit into the theme here are, for example, using raw 4D radar data. So this uses from a 4D radar, the radar cube data. So you can imagine here azimuth, elevation, and range. And then we project that down to a bird's eye view and a front view, and we also fuse it with camera. Run some transformers on that, cross attention. And this gives pretty nice results on this K-radar dataset. So it's a dataset with really tough conditions, snow, fog, rain, etc. And we actually managed to outperform even the best camera plus LiDAR method using camera plus radar. Because, of course, the radar can kind of penetrate through this adverse weather and get really good performance here. And the last paper, last work, is the ongoing work, is trying to bring this all to bicycles. So as I said, hopefully Raoul will drive it someday. So we put free LiDARs on a bicycle, also free cameras, IMU, GPS. And now we're trying to capture data from that. And we're trying to basically develop nice models for perception and prediction and so on to really understand how bicycles move. And this can be helpful for cars, but also, of course, for bicycles themselves to understand that, to optimize our cities for that, etc. And there are many unique challenges, such as the roll of the bike, the fact that the frame is not rigid, so calibration is a mess, and many other challenges. And if you want to know more about that, we can have a chat about that. Okay, so to summarize, my work is about how to collect, annotate, train, and evaluate sensor data more efficiently to hopefully develop more scalable autonomous driving solutions. That's everything. Let me know if you have any questions.
Yeah, hi, Professor Caesar. I'm from University of Delaware. I have a quick question about the neural NCAP. So right now, what we're doing at the University of Delaware is we're trying to standardize a set of simulators that the autonomous vehicle needs to have when it goes through testing. Because if you're just testing using Carla or Unity, the sensor model isn't that good. So we've created a framework that allows all the state-of-the-art simulators to communicate with each other and be synchronized with each other. So and I see in Neural NCAP, you said you use NERF to recreate the scene. So can I ask, how is it that you arrived at this combination of simulators that generated photorealistic data?
Yeah, I think it's just really the fact that we want to synthesize, especially the agent, right? So the environment is, of course, something we could do for a long time. But now with this new generation of NERFs, we're also able to synthesize the agent. And I think that's something we were missing in the past. If you look at the work done by Wabi, for example, Raquel Urtasun, was still room for improvement. So I think it was a natural choice to work with NERFs here. I don't really see what alternatives there are at the moment.
Okay, is this open source already? Can we use that here?
So it's on archive. The code will come out when by the camera ready. So it's under review at the moment, but hopefully in a few months the code will be released. But the NERF itself is called NURAT. That's from the same co-authors. So that one is already available, I think.
Okay, got it. Thank you.
But we can also talk more about that offline.
That would be great. I'll be sending you an email. Thank you.
Okay, thanks.
Hi, Holger. Maybe you can tell us a little bit about, what is the pipeline, an approach Wabi is using?
Yeah, of course, I don't know all the details, right? I just see what I see from their papers. But it's exactly around using kind of learned simulation to train their system, because they say, it doesn't scale to always go out yourself and try to find those strange corner cases that you will never find, right? So rather you should be doing that in a learned environment. That's kind of the general gist of it.
Okay, and then in your case with the the neuro NCAP, how are you generating like these risky or adversarial scenarios? I mean, is there like some kind of a parametric way that you would introduce those, or?
It's actually at the moment fairly hard coded. So the stationary agent, that's the easiest, right? You literally just place a stationary agent. The frontal is also relatively easy if you have a straight road. And then the side road, of course, you need to find a kind of side road intersection. But these are pretty easy. We could in the future, of course, extend this to have some more generalizable scene representation.
But like for the vehicle coming in the opposite direction and taking like, a right turn, that right?
Mm-hmm.
So how do you sort of specify that?
So right now it's really, as I say, basically hard-coded. But if we want to make that more flexible, then yeah, you want it to be a little bit context adaptive eventually, right? So our scenarios were simple enough that we could just, handpick a few dozen scenes where we placed it in there. But if you want it more generalizable, then you probably also want to learn that to some extent where it's a good fit potentially.
Yeah, no, I think it's wonderful. The scale at which you're operating at here is just tremendous. I mean, and it could be very powerful. And I think, one thing that we would like to explore through the CoE is, how can the CoE members, start to like adopt some of the tools you have made, but then we can collaboratively use that for, say, building a safety case. So there is like, working groups in Autoware on the safety cases, on specific scenarios. And I think that would be a very good way of, open development for safety, like that, right? So I think that as we go forward.
So I think that will be a public benchmark at some point in a few months, and then hopefully at least you can test your Autoware developed models there potentially.
Fantastic, great. So let's give Holger a big hand. Thank you so much, and welcome to the CoE.
Thank you.
I'll pass the mic on to Alex. Let me see, where is.
Hi, thank you so much.
Oh, there you are. Okay, sorry, I was looking at the cat, but I didn't see you.
Yeah, sorry for that. Thank you so much, and also pleased to meet you, Holger. Heavy user of new scenes. We've been using new scenes for creating a relationship between objects using graph neural networks, and from that going from real to simulation and so on. So thank you so much. It's been really an amazing work, and very useful for our work. So switching to
actually one second, Alex, I'll just interrupt you before. So I also see Guo Liang is here. So Holger Guo Liang is from Hong Kong, from the university in Hong Kong, and he has outfitted his campus with a lot of sensors at different intersections. And I think that's also quite related to your work in terms of could there be like this object identification, like that approach across the Hong Kong campus, like that, right? So I just wanted to introduce you all here. So, all right. Sorry, Alex, go.
No worries. Thank you so much. So as I think I mentioned, perhaps in a different venue. So for the Autoware workshop, we had a total of 12 papers submitted. From them, the IB review process concluded with 9 accepted papers. So this is the first and the record in the Autoware workshop. So we have 9 papers that we are scheduling to present. As last month, I requested, please, if you are interested to make a presentation at the workshop, please let me know. Try to finalize the agenda as soon as possible. I want to share my screen let me just share my screen now. So I will mention the other topic about the activity in China. So what is this? Okay. So basically, it's an effort between Gordon Pan of Tier 4 and myself. We have been promoting Autoware in China for several years, since 2017-18. And we have organized several activities there. And this time, it was to promote the our activities of the Center of Excellence in several universities in China. So what this trip included is a visit to 4 universities. We initially had a total of 7, but it was difficult to coordinate with them. Some of them changed their availability last minute. So in the end, we had 4 universities. But still looking forward to continue with the conversation with the other universities we couldn't visit. Anyway, the itinerary included Tsinghua University, Beihang University, Lanzhou University, Fudan University, and also we used the opportunity to visit PIX Moving and also Well Dynamic as to also to see the industry side. So in Tsinghua University, we visited the School of Vehicles and Mobility. The leader is Professor Lee. One of their most important topics is communications, B2X. They have a huge project supported by the government. Actually, Tsinghua University is the biggest university in receiving the largest support by the government. And as maybe you know, Tsinghua University occupies the 12th position in the world ranking of universities. So they contacted initially Rahul. They are interested in joining the Center of Excellence, and then we, being such an important university, we extended a visit to them and explained in detail what we are doing, what are the other activities of the Autoware Foundation, and based on their experiences at the infrastructure sensors and so on, they also had a strong interest in joining the Autoware Foundation, possibly participating actively in the related working group, I think in the API working group. So we'll see, we expect to see them joining Center of Excellence very soon. I don't know what are the formalities, or we're going to start the discussion, I guess, with CJ and Rahul. At least I believe that Tsinghua already had discussed on that, so that this is already ongoing. We also visited in Beihang University. Beihang University is already a member of the Center of Excellence. But it's amazing what so many areas they are exploring. Similar to Tsinghua, they are also exploring communications, but they have been using Autoware for a long while. They have been using large language models for predicting accidents and so on. They have, for research for education, a large series of platforms, including a large robobus, different size of vehicles, from small scales similar to F-110 to medium size, full size vehicles, several vehicles, drones, and so on, and also flying cars is currently a hot topic in China. Several companies and the government are putting a lot of efforts on and interest on that topic. Not only just drones that represent that can carry a passenger, but actually a vehicle that can go from land to air. That's what they're currently doing. They are going to contribute the talk at the Autoware workshop. That's also an important part. Then Lanzhou University. They are among the first users of Autoware that I know in China, actively since 2017. I have met several of the students. I've been there several times to give lectures. And and several of their alumni have been occupying important positions in car companies in China. So they have also contributed source code to the Autoware community in the past. During the COVID, well, they got a little bit isolated, but they're very interested in again, stretching out and reaching out and contact, and they are willing to join the Center of Excellence and attend the Autoware workshop and possibly give a talk. This final part is still pending. The one interesting platform is this buggy vehicle that they have there. So fully defined, created by them, everything, mechanical components and everything. And they have been working recently in B2X. So they're also been creating their own devices in the campus, and they plan to deploy that in the city. Then jump again to the east side to Shanghai to visit Fudan University. They will join the Center of Excellence. They are strongly motivated, and it's interesting that we had discussions about the ARM SOFI approach. They have a strong interest in the concept of software-defined vehicle. They, so far as computer science group, they have been so much concentrated in software safety, software validation, safety, and so on. But also they have been interested in the concept of the SOFI approach and how they can be used for software-defined vehicles. After explaining that the Autoware Foundation has a working group related to that, they got very interested, and possibly we'll see them actively, not only in the Center of Excellence, but in the foundation. So that's also an important finding. Then PIX Moving, well, we know PIX Moving. David has been very active in promoting what PIX Moving has done, and how many different options they have for research and industry and so on. So in my visit, of course, I cannot show some pictures of the production facilities, but they were making over 20 robobuses and about 5 PIX kits simultaneously. So it was amazing to see so much technology being produced by them. They use 3D metal printing for the chassis, very strong, and according to different parameters that follow some AI-based algorithm they define. And interestingly, they've been using multi-O-ring based ECUs. So for example, this one in the right is dual O-ring ECU that they're exploring. They already ported Autoware and are considering that. So possibly that would be an interesting addition to the reference working group. And finally, Well Dynamic, I met David there. They have done amazing things, not only with their vehicle and also they have been working on the RoboMart, but they have several developments in innovations in localization, object detection, mapping, and they have an impressive system for multi-sensor synchronization up to the millisecond. So they have not only the DTV platform, but also several options in software that they have created. Well Dynamic works also with both Autoware and Apollo. And just by chance, when I arrived there, the Apollo Summit was being held. Apollo currently is considering to considering again ROS 2, how they are separated from the rest of the community. So we may see more robot-friendly versions of Apollo accessible via ROS. They're considering how to integrate with the ROS bridge and so on. So yeah, basically this this is my the summary of my visit to China. While I was in PIX, I had the chance to meet with Cristian Gariboldi. he is present here. He is a student, master student at the Politécnico di Milano, and also at Xi'an Jiaotong University. He's in a dual degree program. He's been working on with PIX Moving also as an intern. He has also been doing his research there. He has a very interesting topic. We discuss and we try to find a good place to present that and consider that maybe the Center of Excellence is a good opportunity. So if you allow Cristian a couple of minutes to present briefly what he has, I would really appreciate it. That's all for me. Thank you.
Thanks, Alex. This is a lot of very exciting engagements, I think, across China, and I think they have fantastic facilities. And thanks to Gordon for organizing this. And I hope we can have more engagement with the universities from the mainland, and I hope they can participate. I think one of the key things is for universities or members to participate in these member meetings. So just yeah. So and I think just going back, Alex, to the
Yes.
to the Autoware workshop. Could you just share how many speakers are confirmed, how many contributed papers will be there, and then I think in the course of the next week we can share with everyone the program, right? At least a draft program, because we still have some time. But
Yes, correct.
I just the main reason I'm asking that is because then if we need to, get more other members from the CoE, we can fill up the agenda in this way, right? So.
Yeah, the agenda is currently an interesting challenge because the foundation also would like to see some industrial members joining the workshop. So wait, hold on a second. So currently we have 9, 10, 11, 12 talks confirmed. 12 talks confirmed, including the papers presentations, and so 12. Sorry, 15. Sorry, 15 presentations confirmed that need to somehow squeeze together in the one day workshop.
Yeah, that's good. That's good. I think our mode last year was also we had a lot of back-to-back presentations, and then Holger, I suppose you will also be attending IV.
No, I will only be
Okay.
at intern.
Okay, but you have some of your team from TU Delft attending.
Not sure. I would have to check.
Okay. I saw you have some papers in IV 24.
Yes. So some of our students for sure, yes. Yeah.
Okay. Yeah. You can encourage them to come for the workshop if they have time that day. Yeah. Great. So Alex, we can work on the draft program, and then Sumit has already reached out, so we can start to put that together, because I think this will be a very exciting workshop this year, especially since people will be there in person. Yeah.
Correct. Thank you.
Yeah. Great.
And if you allow maybe a few minutes to Cristian to present.
Yeah, of course. Please go ahead, Cristian.
Okay, hello everybody, and nice to meet you. I'm very excited to see that also Holger Caesar is here, as my work is a integration between NuPlan and Autoware. So I will share my screen right now. I have some slides to share. Okay, please give me a feedback if you can see the screen.
Yes, good.
Okay, so my work is, I was working, thanks Alex for the introduction, by the way, and I was working in PIX Moving, and I'm still working in the planning department, and I developed a hybrid imitation-learning based motion planner, trained with the NuPlan dataset that I will skip the introduction as Holger already did a great presentation. But the reason why I chose the NuPlan dataset is because, according to this paper, actually is one of the most impactful open source dataset. And the second one is Xi'an. So I think it was great for my application. And the simulator offers some metrics, open loop and closed loop, which are great for evaluating the planner, for imitating the human driving style, and also to check if it has a safe closed loop driving. And these are the metrics. And I analyzed some baselines, and I checked that we can recognize a pattern. So we have some learning-based and ruled and sample-based planner here. The first three ones are learning-based planners, and they are excellent for imitating the human driving style, as they can score a high open loop performances, but they cannot provide a safe closed loop driving. Also, as Caesar said before, if you try to evaluate them in unseen scenarios, actually their performances drop dramatically. But on the contrary, instead, rule-based and sample-based planners cannot imitate the human driving style, but they can score high closed-loop performances. And that's why I decided to build and design a single planner that can provide both high open-loop and closed-loop score by combining learning-based and optimization-based planner. So on the left, I developed this learning-based planner, which is integrated with the ROS2 environment with a ROS bridge. And within the ROS2 environment, I'm using the MPT, which is Model Predictive Trajectory developed by Autoware. And okay, these are the details about the blocks you can see in this scheme. But the important thing is that the planner provides a center line, a path, and the multi-layer perception is going to optimize that path in order to minimize an L2 distance between the human trajectory and the one that takes as input, so that it can output a human trajectory. And then it gives the trajectory to the MPT, which is going to optimize it and make it safe, safe for driving autonomously, actually, also for unseen scenarios. And I tested this planner in the ROS2 simulator because I think there are some advantages in doing that. The first one is that the simulator has the same control and planning algorithms as the real vehicle, because my final goal was to apply this planner to the real vehicle. And the second reason is that by evaluating this model in the ROS2 simulator, I could use different maps, different scenarios, so I could test the generalization and robustness capabilities of the model. And I think there are two limits about the NuPlan evaluation metrics. Maybe we can discuss it later if we are interested. The first one, I think, is that the NuPlan evaluates the ability of the planner to perfectly imitate the trajectory of the human driver in that specific scenario. But personally, I think we can achieve very good human trajectories, even though we don't perfectly imitate the one in the simulator. And the second one is that the NuPlan evaluates the predicted trajectory, but not the one actually traversed by the ego vehicle. And since I wanted to develop my model for the real vehicle in the Autoware environment, this is the Autoware planning component structure. So we have a mission planner, a behavior path planner, a motion planner, and in the end, we give the final trajectory to the control components. So what I did is the following thing. I added this block between the behavior and the motion planners so that we can take as input the behavior path, and we make it, we optimize it in order to generate a human trajectory, which is given to the motion planner, which is the optimization-based planner. and it can optimize it and make it safe. And these are some experimental results. So the green trajectory is the neural network trajectory, and the purple one instead is the one after the optimization process. And I did several tests in different maps for different scenarios. And as we can see, the neural network cannot remain inside the boundaries perfectly, but instead, after the optimization, we have a very good behavior and trajectory. So, okay, this is just other tests and simulations. I will go fast here. These are just some pictures about how the learning-based trajectory is optimized by the MPT in order to remain within the boundaries and to be a very good one also in closed-loop driving. I also tested some obstacle collision avoidance scenarios. So in the simulator, you can place some pedestrians on the street and see if it crash or not. As expected, the car stops, and if you remove the pedestrians, it starts again. I also tried to do an adaptive cruise control test by placing a car in front of us, which is slower, and to see what's the behavior of the planner. So as expected, the car lower down, and then when the car changes lane, the ego vehicle starts again. And I also collected some qualitative results between the default Autoware planning components on the left and the hybrid imitation learning planner on the right. So on the top, we have the velocity profile together with the trajectory. And on the bottom, instead, we have the acceleration profile. So as we can see on the left, which is the optimization-based planner, the default one of Autoware, the trajectory is pretty much a center line. And also we can see that the acceleration profile has some peaks. But on the right instead, we can see that the trajectory is a bit more human, like the turns are smoother, and also the acceleration is not that high. But in other scenarios, the difference is bigger, like here on the left. The optimization-based planners are very geometrical. They follow almost the center line, while the learning-based, the hybrid planner, actually during the turns, just takes a larger turn in order to minimize the acceleration profile, also, as we can see on the bottom. Here, it's more evident, the difference, as on the right, we have just a single turn to go, but on the left instead, we can see that the planner just takes the center line. And these are other results. I collected many results. This is interesting as this is the adaptive cruise control test. And we can see that the default planner of Autoware actually accelerates a lot. And then when it sees the obstacle, brakes with a high, I mean, the deceleration is very high also for the braking. But instead, the hybrid planner on the right has a smoother velocity and acceleration profile, which is more human-like. And I also did some real-world tests on this L4 autonomous vehicle that we developed in PIX Moving. And it works pretty well also in real-world scenarios. And I did several tests, but of course, I couldn't test the vehicle in so many different scenarios, as we just have this kind of place where to test the vehicle. But I noticed that the planner works well at low speeds. When we try to increase the speed, actually, it becomes unstable, as we can see here. And I think that the reason is noise. So I tried to introduce some noise in the simulator as well to see what's the reaction of the planner. And this is the result. So if I add some noise in the simulator for low or high speeds, we can have unstable trajectories, as we can see in these results. So these are the results without the noise. Actually, on the left we have the Autoware planning, and on the right the hybrid imitation learning planner. And we can see the trajectory is more human-like. Also here, when there is a step in the drivable area, the optimized planner just tries to follow the step, but instead the learning-based hybrid planner ignores the step of the drivable area and goes straight. And these instead are results with adding the noise. The noise is a Gaussian noise, and with high speed on the left, we have a very unstable trajectory, like in the real test with the robobus. When instead the speed is low on the right, the trajectory is not very good, but it's not as unstable as the one on the left. And we can notice the same thing with the acceleration profile, as you can see here. And I also plot some velocity profiles and acceleration profiles in all the scenarios. So the default planner of Autoware, on the top left, this instead is the hybrid planner. And these are the velocity profile with the noise for high and low speeds. So, and this is for the acceleration. So yeah, this is the research I'm doing in PIX Moving, and I was excited to present it here today, since there are people from both Autoware and NuPlan. And I'm open for any kind of feedback or discussion, but I think it will be interesting maybe, since I know that in Autoware some people are working in learning-based path planning, and but so far we just have sample and optimization-based planner. So I think this integration could be interesting at least. And thank you very much for your attention.
Thank you so much, Cristian. I think it's amazing that you got IL working for real. I think that's also very brave and bold, but it's really quite something to see it operating for real. And this you did as your master's thesis, or what did you?
Yeah, actually, I'm doing an internship in PIX Moving while I'm working for my master thesis, and this work is supervised by my professor for the master thesis. Yeah.
Okay, that's fantastic. Yeah, I think the safety issue obviously will be critical with any IL-based approach, but yeah. Does anyone have any quick questions for Cristian?
Yeah, very briefly, Cristian, and great work. I'm just curious. And what really blows my mind here is that you talked about the real vehicle and the PIX Moving and the robobus, and I guess we'll have to improve our internal communications. It's the first I heard of it here at PIX, but it's wonderful. How did you do that, or how was the experience with the actual vehicle? Could you just say a few words on that?
Yeah, for sure. So I mean, with the real vehicle, as also I proved with the results, actually it's good, especially at low speeds, as the neural network take as inputs some data from the localization directly. So it's very sensitive to noise. And when you try to increase the speed of the vehicle, actually the trajectory becomes unstable, and you can feel it on the real vehicle. But I think it's easily, there is an easy solution for that. So there are two ways. One is that maybe you can try to design some filters, filter out the noise, but in my opinion, it's better maybe to introduce some noise in the training data so that the planner can learn how to generalize better for high speed as well. But yeah, the final goal of this project is to have a more human-like trajectory for the real vehicle, which can have some benefits in the autonomous driving. But overall, the results are good, I think. And now the next goal is to make it more stable, even for higher speed.
And you did this in the parking lot at PIX in China, or where did you get exposure to the vehicle itself physically?
Yeah, actually, I am in China, in Guiyang, and the tests I did were around the factory. So we have the permission to test some algorithm in this real street where there is real traffic. It's around maybe 5 kilometers probably, and yeah, it's better than nothing.
So last question, did you use the remote control to toggle between control of the vehicle, or did you ride on it during testing?
No. The testing was real. So it was running with the autonomously with the algorithm. Yeah.
Were you on board?
Yeah, I was on board, and
Excellent.
during the first test, I didn't know the vehicle would be unstable for higher speed, and I fell down because yeah, the vehicle like stopped abruptly, and I didn't expect that. So it wasn't a very good experience, but worth it.
A very valuable learning. Great job. Thanks.
Thank you.
Cool. Thank you, everyone. We are at the end of our hour. I mean, there's much more to talk. We didn't get to chat with Jack and Christoph and Guoliang and Daniel, but I think we'll stop here for today's meeting, and then we'll get to see many folks at ICRA in the coming month, and then at IB again, and we'll start to plan that out. And thank you, Holger, for a wonderful talk, and Cristian, amazing to see in a master's thesis you're able to get a real system up and running. Yeah.
Yeah,
right.
impressive.
So
everybody, thank you. Have a great day.
Yeah.
see you at ICRA.
Bye.
Thanks, Jack.
Talk to you
Yeah.
soon.
Bye-bye.
Bye.
See you soon, Christoph.
Bye.
Bye.
Thank you. Bye-bye.
Bye.
Bye.